Thank you very much, Teresa, for this introduction. So let me try this. Yes, good. So I'm going to, so first, when I was asked to give a course here, I thought I didn't really have anything to tell you because there has been many courses over the years, and most of what I know has already been given in courses. So I decided to choose something more recent, which is the work we did with Alaa during her thesis. Alaa is somewhere in the back. Yes, so maybe you wave your hand. She's over there. And so it's not a course on the thesis, but when you work on a thesis, there's a lot of material around. So I'm trying to show you the landscape, and the landscape is really beautiful, according to me. So I'll try to convey some of this beauty. What else do I have to say? Of course, if you have questions, ask your questions. I may not be able to answer, but you can ask. And I've put the slides for what we'll see today. They're available on the web. I like it when I attend a talk to have the slides with me, so you can go back and, well. And it's part 1 here, and part 2 is not yet there. It's not completely ready yet, but it will soon be there too. Okay, so I will start with a long introduction, almost an hour. So it's not yet really in course mode, so no definitions, no proofs, that will come later. And let me start with examples. More or less natural examples where positivity or inequalities are not obvious. They've been proven or not by hand. And the question is, what can we do with computer algebra? So, I was warned. You're missing only the border of a 2, so it's a 2. It's not so important. So this sum doesn't look positive at first glance because there's this -1 to the -27 to the n minus k, so the terms oscillate, so it's not completely obvious that it's going to be positive, but it's been proved positive by Straub and Zudilin a few years ago, 10 years ago. And it turns out that this sequence satisfies a nice recurrence, and that will be our starting point. Another one, it's actually a family parameterized by an integer k. Again, it's oscillatory. There's this -1 to the j. And this has been conjectured first to be positive for k at least 4, a long time ago. And then there was a proof 6 years ago on arXiv. And again, it's nice for us because it gives a family, so if we have algorithms, we can try to push them as far as we can. And for each k, it turns out that there's a linear recurrence of order k with polynomial coefficients whose degrees grow with k. More examples. There's this nice result by... no, I cannot. I don't know how... Aha. Okay. Yes. I'll try. I'm not sure I can do it, but I'll try. But I've been warned that there was it's not really a problem on my machine, right? It's the screen that's too wide. No, it's the projector that's... No, I don't know how to do it.
Let me organize, solve the problem.
Okay, no, I don't know how to do it. So you're losing one letter. Okay. So this is a power series, product of 1 minus ci x to the mu I. And for those choices of the ci and mu I, the coefficients are all negative except for the first one. And again, there's a simple linear recurrence for these coefficients of order k, so that's another family. Another one, which is due to Aline. Aline keeps sending us examples where we should be that we should be working on. So this is one of his. You take this power series solution of, there is a power series solution of this with S0 is 1, and it has positive coefficients. And again, there's a linear recurrence, it has order 2, coefficient of degree 3. Aline provides 2 proofs. So I write Boston 2020, but it's in a paper by Boutillier and Rachel, and Aline wrote the appendix with these proofs. So here's 2 proofs that use nice techniques, but not what we're going to do. Would you say that your techniques are computer algebra, automatic? Partially automatic. Okay. Another one, Dodsenko and co-authors. This it's really similar to that. You have a power series of the form x, h of x to the 7, and h has positive coefficients. And again, there's a recurrence. For the proofs, the nature of this one is a bit harder, so that's why I'm showing it, although it looks very much like the other one. Other examples are, I wouldn't say more practical, it's really cheating. So maybe the first one is, it's in a paper with Miura, but really the general question is this: when you have a, I see the problem. Okay, tomorrow I'll try to prepare my slides to be more inside the slides. When you want to sum numbers numerically, it's better if they all have the same sign, because then you don't have cancellations, and numerically it behaves better. So in this work, we had a recurrence of order 4 with coefficients that had only degree 1, but 2 parameters, and the question was to show that the sequence of coefficients was positive. So there is a proof by hand, and again the question is, can we automate this? And the second one is, forget about it's presumably about the shapes of blood cells. But in practice, it's really, you have a linear recurrence of order 6 with coefficients of degree 11, and the question is UN positive? And is Mark around? No. And Mark, who is not around, with Still-Melzer, gave a very nice proof of it using complex analysis. An automatic proof, using numerical, reliable numerical evaluation. And then there was a proof by hand by Aline and Sergei over there. So really the subject of the course is, what can we do automatically? Which of those can we really be like this, which are harder and which are out of reach? So as you've seen in all the examples, I've mentioned that there was a linear recurrence, and this is our playing ground. So let me just give one definition from now. We'll say that the sequence is p-finite if it satisfies a linear recurrence with polynomial coefficients. The order will always be d, that's my notation. And the coefficients will, most of the time, be rational numbers, and sometimes fractions with rational coefficients. And those are incredibly common in practice. So, of course, Fibonacci numbers, fn plus 2 is fn plus 1 plus fn, but also factorial n, 1 over factorial n, the central binomial coefficients, the Catalan numbers, and it's estimated that in this encyclopedia of integer sequences, about a quarter of them are p-finite. And now there's the online encyclopedia of integer sequences, but the proportion should be about the same. And what else? I will always assume that P0 is non-zero, otherwise you can reduce the order, and that the leading coefficient, PD of n here, does not vanish on the integers. Because if it vanishes, you cannot define un plus d in terms of the previous ones. So let's assume that this doesn't happen, which is not an issue. Because if we're trying to prove positivity, the roots of the leading coefficients, there are only finitely many of them. It's a polynomial. So you can unroll your recurrence till you reach this root. You check that the previous ones are positive, or in your direction, the previous ones are positive, and then you start working there. Okay, so our data structure, our input will be this, the recurrence and initial conditions. So just to be sure, but you've had a course 2 years ago by Christophe Kuchan on those kinds of questions, but just to make sure that we really know what we are talking about, let's start with a quiz. So what's your guess? Let's start with the first one. 1 over binomial 2nn. Who thinks that it's p-finite? Raise your hands. Pierre, the question is about this one. I see that you were not attentive. Ah, ouais. Okay, who thinks that it's not? Okay, so let's see. So let me write UN is, sorry? Oh, et si j'écris gros? Okay, so this is the question. So this is 1 over, so that's 2n factorial, and that's n factorial squared, okay? So if I write un plus 1 over un, what do I have? I have n plus 1 squared, and I have 2n plus 1, 2n, okay? So I have that, oh, tac, tac. So I have that 4n un plus 1 minus n plus 1 un is 0. Okay? So p-finite. P-finite. Next. This one is more difficult. Cosine n. Who votes for yes? I have many hands for yes. Who votes for no? I have many hands for no. And you're both right. So, so there is a recurrence. So you have that cos n plus 2. So I don't know if you know them by heart, but there's this cos a plus b, which is I will check my notes. Also, I have a cold. I'm not in a good shape. 2 cos 1 cos n plus 1 minus cos n. Let me check. Exactly. So this is a sort of linear recurrence, but the question is, I didn't say anything about the coefficients. So is this in K? So depending on K, on your choice of K, it's either p-finite or not. Okay. The floor of log n. Take log n and you take the largest integer below log n. Who thinks it could be p-finite? Well, the question is phrased in such a way that nobody thinks that it could be p-finite. And the reason is that you have large periods where it's stable, it doesn't move. And with a finite order recurrence, you cannot really do this. 2 to the 2 to the n. Very simple sequence. Who votes for p-finite? P-finite is not very popular nowadays. And you're right, it's not p-finite, it grows too fast. If you think it could be in a recurrence, then you have n becomes n plus d, That's much larger than what the other ones can even together reach. So it's not. The harmonic number, who votes for yes? Okay, so you've understood. Oh, sorry, who votes for no? So and the reason is, if I call that un, then you have that un plus 1 minus un is 1 over n plus 1. So you multiply everything by n plus 1. And then you shift this, equals 1. You shift this and you subtract. So you have n plus 2, un plus 2, minus n plus 2, un plus 1 is 1. And then I do plus 1, minus 1, and you get rid of the right-hand side. So this one is p-finite. And the last one is also p-finite, but it's more difficult to see. But you know it if you were in the course by Christophe 2 years ago. So there are algorithms to take as input such a binomial sum and produce a linear recurrence for it. So this is the kind of sequences we'll be working with. And why are those interesting? Because they have a lot of properties, but there's one that will be very useful, which is that they are closed under multiplication by a constant, here, summation, and product. Multiplication by a constant is clear. It's a linear recurrence. You multiply your sequence by a constant and you get the same equation. For sum and product, maybe I thought I could illustrate this by just one example. I'm sorry. Mais il demande technologiquement il est plus avancé. So the thing is, so you have your Fibonacci numbers, and you want to prove that this sequence is nice, where for us nice will always mean p-finite. So the idea is every time you see an fn plus 2, you rewrite it on the first two. So that's fn plus 1 plus fn minus fn plus 1 squared. Okay? Now you write un plus 1. So I have an fn plus 1 fn here, which becomes an fn plus 2 fn plus 1. Then plus fn squared will become an fn plus 1 squared. And then minus fn plus 1 squared will become a minus fn plus 2 squared. So again, every time I see fn plus 2, I rewrite it. So I get this. And you see, when I'm going to expand, everything will be linear combination of fn squared, fn plus 1 fn, and fn plus 1 squared. So I know that after a finite number of steps, I will find the linear dependency, because everything is rewritten on 3 vectors. And it turns out that here we are lucky earlier, unless I made a mistake in the computation, which is entirely possible. Maybe not, I don't know. So I get 2fn plus 1 squared here, plus fn plus 1, minus fn plus 1 squared, minus 2 fn plus 1, minus fn squared. So fn plus 1 squared disappears, fn minus fn plus 1, I get a minus here. So I get that I made it, so I get, in the end, fn plus 1 squared minus fn plus 1 minus fn squared. And if you look here, you see that it's exactly minus un. Okay, so you found a linear dependency, and you've proved Cassini's identity. Oh, no, you haven't proved it. You have to check one initial condition. I leave it as an exercise. And this, what we did here, is the general proof. So well, it's a course, so I'm supposed to give proofs, so let me give one proof. You start with your two recurrences. I'm going to show that the product of these sequences, an and bn, satisfies a recurrence, a similar recurrence. Oh, I've said that I took the hypothesis that this was okay, so yeah, you can forget about this part. So you can rewrite an plus k in terms of the previous one. No. For any k, using this kind of technique, you can rewrite an plus k in terms of an up to an plus d minus 1, the order. Right? Same for bn plus k. So when you do the product, you'll have a finite number of products of an plus I, bn plus j. So at one point, there will be a linear dependency. This linear dependency is over rational functions in n. So it could happen that the leading coefficient, when you reduce to the same denominator, has a polynomial in n that vanishes at an integer. So you get that for some k, there is a recurrence that's satisfied from k onwards. And I cannot just say, okay, but I can shift. No, at that stage, it's not allowed anymore. So I really need a recurrence that's valid for n starting at 0. But there's a simple trick for that. You take your recurrence, and you multiply everything by n minus 1, n minus 2, up to n minus k. You still have polynomial coefficients, and then everything is 0 before n equals k, and then the recurrence takes hold. So that's the proof that all sums products will be nice. And it's not only a proof, it's an algorithm. Because you will write everything in this basis or set of generators, put that in a matrix, and keep doing this until the matrix has a non-trivial kernel. You add rows. The first one is un, that you rewrite in your basis, then un plus 1, rewritten, and so on. And once you have more rows than columns, there is a kernel. And you can compute it. So by these properties, what you get is that there are many things that you can reduce to positivity. If you want to prove that sequence is increasing, you compute a recurrence for un plus 1 minus un. You just have to prove that un plus 1 minus un is positive. Same for convexity, log convexity, or more generally, you have two sequences. You want to prove that un is larger than Vn. You compute a recurrence for un minus Vn, and you prove positivity. And the context where this takes place is that we like p-finite sequences and linear differential equations as well very much. So there's a large body of algorithms around these notions. We know how to compute such data structures from polynomial equations, algebraic power series, satisfy linear differential equations, so their sequence of coefficients is p-finite. Diagonals, I think, are there? Did anyone give a course on diagonals in JNCF? Aha, so maybe next year. Definite sums and integrals, and there was the course by Christophe Kuchan was about this 2 years ago, how you compute linear recurrences or differential equations for definite sums and integrals. And once you have this as your data structure, you can do numerical evaluation in a reliable way, and there was a course by Mark, who's not there, last year. You can compute local and asymptotic expansions easily. You can prove identities. Sometimes you can compute closed forms, and that's differential Galois theory, and maybe there's been a course on differential Galois theory a few years ago. But that's not what we want. We want to go the other way around. You have a closed form, and you cast it into an equation that it satisfies, and we'll work with the equation. And then there are inequalities, and that's what I'm going to talk about. Okay. Are we clear so far? So let me start with bad news. Even with constant coefficients, the question is not simple. With constant coefficients, what you know is that you have a closed form, right? This is something we learned very early at school. You take your recurrence, you call this polynomial the characteristic polynomial of the recurrence. You look at its roots, and what you know is that the general solution of this is of this form. So you have powers of the lambda i's that are the roots of the characteristic polynomial. Sometimes, because you'll see later why I will mistakenly call them the eigenvalues of the recurrence, but that's what they will be soon. And so you have powers of the eigenvalues multiplied by polynomial, and the polynomials can be computed from the initial conditions. So there was one situation which is nice. It's when lambda 1 in absolute value is larger than all the other ones, and the corresponding coefficient is non-zero. Because then, at one point, this will dominate asymptotically. And then, since those are only polynomials, you can even bound the point where this happens. So you have a positivity proof. So this is the simple situation. And that's the situation that we'll try to extend to the case of polynomial coefficients later, where it's still simpler than the general case, but it may be hard in certain circumstances. So you have two conditions there, one which is related only to the recurrence, and one which is related to the initial conditions. And that dichotomy will take place also in the polynomial case, in the case of polynomial coefficients. So let's start with an example in this situation, this simple situation. It's an example, again, pointed to us by Aline, from an exercise in the American Mathematical Monthly. The question is this: you're given this rational function, you expand it in Taylor series at 0, show that that's here. Show that the coefficients are all positive or non-negative if and only if A is at least square root of 3. So this is computer algebra, so let's do it. That's bad. Don't worry. Okay. Can you still read me in the back? Okay. So the goal is to show that the Taylor coefficients of this are positive or non-negative for A starting at square root of 3. So it's actually non-negative here. So you take G, and we look at the first few coefficients. Let me make it clearer. Okay, so you see first that this A square larger than 3 is a necessary condition because of the coefficient of Z squared. And also we need A to be positive because of the first coefficient. So you need a larger than square root of 3. So that's clear. So now the question is the other way around. So let's look at the linear recurrence satisfied by these coefficients. Since it's a rational function, you can do what you want. Okay, so the recurrence is there. There's an implied equals 0 in this. So this is the recurrence, and those are the initial conditions. You have 4 initial conditions. So that's because the recurrence doesn't start immediately. And that explains why that explains, I don't know. Maple's R-solve is unable to do this because it doesn't like those many initial conditions, so it returns, no, I don't know, I don't do anything. So, but there's a function in this wonderful package that takes your rational function and gives you the general formula for the coefficients. And it will be clearer if I get rid of those root-offs. Oh, no, let me do better. I want to prove it for n larger than 2. Yes? Yes. No. Look at the solution here. So you have this general formula, but the first 2 cases are not yet of the same shape. So how the recurrence is written? It's actually the recurrence of order 4, but you simplify it to say. No, it's really it's better to write it. You can do what you want, but it's better to write it order 2 and then you multiply by nn minus 1. Okay. So the thing is, it's a rational function, but here the numerator has degree slightly larger than the denominator, and that plays a role in the initial conditions. Okay, so we have this formula. It's not completely clear yet that this is positive for all n larger than 2. So then you need to do some analysis, right? So what's clear is that, and this is to the minus n, so you should look at them the other way around. So this is the larger one. Subtract, but you take to the minus n. And this is the smaller one. So what we expect for this to be positive asymptotically is that at least this will be positive. Otherwise, it cannot be positive. And then you have to fear that this one might be negative, and it's the case. So then you have to check, starting with it, when does this one start to dominate the other one? And once it dominates, it will dominate forever. But we are only computer algebraists, so we need to use what we have. So let me cheat. No, I mean, this is something I always tell students not to do, which is copy-paste. So I take this, I call it x1, and I take the other one, I call it x0. So x1 is the big one. And let's call it coef. No, not coef, because that's already taken. Okay, so x1, first I have to check that the coefficient in front of x1 is larger than, it's positive for a at least square root of 3. There's this square root of a squared minus 3 in the denominator, so, but those are only algebraic numbers, so you can simplify this a bit. N. No, yes, no. So this is, oh, and then normal maybe. Okay, so, oh, that's almost nicer, but you see, now you see better because I want first to show that this part is positive, but there's the square root of a squared minus 3 here, and this should be it's amazing. I did this example tons of times. It works. So I don't know. Let me check what I. When you don't know, you plot. You can factor. Here, you want to factor? Simplify. Yeah, there are lovers of simplify. No, that's good. But it tends to infinity, which is not good. No, okay. No, that's good. So I'll do it in 2 steps. But it looks positive, at least, because the lower bound is 0.5. So let me first show that it's positive. It's positive. So there's magic here related to what they know about algebraic numbers, but it's positive. So now I just have to look at the point where this formula starts to be positive, and from then on it will be positive. Let's just look at it for, let me call that CO0. And I will just do it for n equals 2. And then you see that it's positive for a larger than the square root of 3. So we have proved positivity of the sequence. But it's messy. It's not so easy. Right? But that's an example where one of the roots dominates, and then it should be easy.
So when this kind of examples are proposed in such, I think it's a journal, right?
Yes.
Do they expect any kind of proofs, or they have in mind to use some certain techniques?
No. No, it's really a journal for math teachers. So anything that's more or less rigorous. Done. Okay, so for this type of recurrences, when you have this property of domination of the largest root, that's okay. But it has to be difficult because there are difficult problems around that reduce to positivity. And the Skolem problem is probably the most famous one of those. And that's this problem. You're given a linear recurrence with constant coefficients, and say the coefficients and the initial values are rational numbers. And the question is not positivity, is there a value of n where un equals 0? And as I write in the bottom, it's only known to be decidable when the order is at most 4. And that's a result by Mignot and co-authors in '84. But there's a reduction from this problem to the positivity problem that I'm going to show. So first, you take the LCM of all the denominators that are around, and you construct the sequence m to the n un. By closure, m to the n is a solution of a recurrence of order 1, so you get a linear recurrence for this sequence. So you get a recurrence for this sequence Vn by just the product of 2 solutions of recurrences. And now you have a sequence of integers. And it's 0 if and only if un was 0. Now you will, now it's easier for integers to detect 0. Because you're going to construct another recurrence now for this sequence, Vn square minus 1. Again, by closure property, you can get a recurrence. And now, if un is 0, then Vn is 0 and you get minus 1. So Vn is not positive, and conversely, if Vn is positive, then Vn square is larger than 1, then Vn is larger than 1, so un was not 0. So you have a reduction to positivity from this difficult problem. So in general, we are dead. We cannot hope to solve those problems with elementary tools, at least. So what do we know for, not for the Skolem problem, but for linear recurrences with constant coefficients? There's been a lot of work, in particular by Waknin, Worrell, and many of their co-authors. So what do we know? We know that positivity is decidable in general for order at most 5. If, moreover, the characteristic polynomial is square free, there are no multiple roots, then we have a decidability for order at most 9. If it's a sequence of integers and it's reversible, it means that when you unroll the recurrence backwards, so you produce u minus 1, u minus 2, and so on, and you still get integers, then you have decidability up to order 11. And then if you have both characteristic polynomial square free and reversible sequence, then you have decidability up to order 17. So that's, and it's many papers in the past 10 years on those questions. So there are difficult problems around, and here is a simple difficult problem, if I can, simple example of a difficult problem. It's an example that was shown around by Waknin for 5-6 years. You take this very elementary sequence that fits in one line. It's a sequence of integers. I is the I of the complex numbers. But this is a sequence of integers. It's not difficult to compute a linear recurrence that it satisfies. It's constant coefficients order 10. And then if you plot un over 65 to the n, you see that it looks positive, right? Up to n is 1,000 or so, but then they compute it much more, of course. The first million elements are positive. And the question is not, is it positive? Everybody is convinced that it is positive. But come up with a proof. Nobody has a proof of this positivity. So this, I'm showing this to you because this is the kind of problems we don't want to look at. Because we are going to go to a polynomial coefficient, so even even with constant coefficients we cannot do it, it's not for us. Okay. So that's what's known for constant coefficients. Yes?
Is there any undecidability result on some subclass?
No, not that I know.
Where does this sequence come from? So
You mean why this one?
yeah.
Because you saw I showed you when there's one root that's larger than the other ones in modulus, and it's easy. So in this one, you have many roots of the same modulus. So you have an oscillatory behavior.
Somebody comes up with this because it's looking.
Yes, yes.
Because the norm of 4 plus 7i and the norm of 8 plus 1 are both equal to 65.
So they are all on the same circle, except one that's inside the disk. Okay, so what about polynomial coefficients? What do we know? There's a nice algorithm a few years ago by Gerold and Kowers using quantifier elimination. So what they do is you construct this formula. Un plus d is positive, and sorry. Construct the formula for all n positive, for all un positive, for all un plus 1. So you forget that the ui's are related by a recurrence. They're just variables. They're all positive, and the question is it the case that if they're all positive, then the next one will be positive as well. So a sort of proof by induction. Okay, I see with your eyes that it's not clear at all, so I'll give you an example. The thing is, it's not completely an algorithm, but it proves positivity when it terminates. Because you do this you look for M such that, but M might not exist. So let me show you an example that was really beautiful in their paper, because it's not so easy. You take the Legendre polynomial. You don't really need to know what they are, but they satisfy a linear recurrence. And you look at the plot on -1, 1, since this is Turan's inequality. You look at the plot of this for x between -1, 1. It's an even function, so you don't need to bother about the part you're missing. It's the same as this. Okay, and again, you want to prove that this is positive by induction. So let me try this. Start with a basic example of quantifier elimination, if you've never seen that. Everybody takes the same example. There exists x such that ax squared plus bx plus c is 0. I think that's the syntax. And you get many things, but the one which is interesting to you is this one. If a is different from 0 and b squared minus 4ac is positive, then there are real roots. And then there are special degenerate cases when a equals 0. So that's what quantifier elimination does for you. It finds conditions under which you have a solution. So let's start with Turan's inequality, and this is the recurrence that the Legendre polynomial satisfied, and I will rewrite Turan like this. So first, a natural question is, if I have arbitrary Pn minus 1 and Pn, I don't know what they are. They are not even related to Legendre polynomial. Is it the case that this? Yes. Yeah, the quantifier elimination maple is not the best one. I'm told that Mathématiques quantifier elimination is much better, and I will not rely on quantifier elimination, Maple's quantifier elimination in this talk. So let's construct a formula whose unsatisfiability, so there's no solution, would prove the inequality. So let's look at the formula. The formula is, no, I can do it like this. -1 is less than x is less than 1, n is larger than 1. The first three values are related by the identity for the Legendre polynomials, and we're not lucky, or we are lucky, Turan's inequality does not hold. So if there is a solution to this, if there's no solution to this, it means that I have proved Turan's inequality. You see, because it cannot be negative, so it has to be positive, or non-negative. So let me separate in two parts the inequalities, and now I replace this Pn plus 1 by variables. Now those are indices. P0, P1, P2 are arbitrary variables. So they are not, the only information I have on them is that they are related by the equation I give here. So is it the case? Quantifier eliminate. It's not fast. With my previous Mac, it took 30 seconds there. But still, it's slow. So what I will be using in this talk is this SAT modulo theory external package that they use with Z3. That's really fast. So you get true. There is a solution. So we haven't proved Turan's inequality. So now you go one step further. You construct a more complicated formula where it starts the same. Now you introduce Pn plus 3, and then you say the first one was positive, but is it possible that the next one is negative? And if it's not possible, then I have proved inequality. Again, I replace this by variable. I kill quantifier elimination. I use this SMTlib, and it's false. So we have proved. So what have we proved? We have proved that if it holds at n equals 2, then it will hold forever after. But I still have to prove the initial conditions. So you look at the first ones, and then yes, they're all positive, so that's good.
But if the SMT solver says false, you don't have a certificate.
No, you don't have a certificate. That's a very good point. Thank you very much. So it's nice. We have a proof, but you know, when it runs for 2 days and you just get false, you're always suspicious. Was there a bug? How can I know? So certificates are good for that, for peace of mind. Okay, and it doesn't always work. I'm running a bit late, so I will skip this example. It's a very simple example of a recurrence with constant coefficients. And for this, it runs forever, and it's not difficult to prove. And of course, they noticed this, Kawers, Gerold, and Veronica Pilwein as well. And they found a way to avoid those difficulties like this, which is to add an extra hypothesis. So on top of instead of you asking that the previous ones are positive, you ask that that ui plus 1 is larger than mu ui for some mu, positive mu. So you give more constraints. So you have a cone that you cannot really see here, where you expect un plus 1 to stay. Or in more dimension, un plus 1, un plus 2, you want them to stay in that cone. So you construct this formula, and you cross your fingers. So let me just do it once. I'm going to do it with a larger example with polynomial coefficients. So you look at the first coefficients. Maybe I should display them. They're all positive, right? But it's not what you're interested in. You're interested in ui plus 1 larger than mu ui now. So you look at the ratios. Let me hide this again. Now you see that the ratios tend to be larger than at least 3 ui. So I will take mu equals 2. So I take this formula and mu equals 2, and I want to show by induction that if ui plus 1 is larger than 2 ui and so on, then we're okay. So you do exactly as before, right? You add this inequality, you construct your formula, and you say false. So you found a proof easily. And actually, I'm not going to spend time on this, but they also find the mu by quantifier elimination. When variables are free, you can do a lot. Okay, so the idea is add a hypothesis and prove with this hypothesis. So there's an example that I will be using a lot, which is this sequence. That's the first one, the first sum by Straub-Zudelin, and that's the corresponding recurrence. It's the same 2 that's truncated here. And that's an example where the vanilla Gerold-Kawers method does not work. It does not terminate. So you add an extra hypothesis, say Sn plus 1 larger than 18 Sn. And then it's very easy to get a proof. You write Sn plus 2 as Sn plus 2 minus 18 Sn plus 1, and you add what you've subtracted. And you see that this, you have 2n plus 2 squared, so that's positive. Here, that's positive. Here, that's positive by induction. Here, that's positive. And here, that's Sn, which is positive. So by induction, we have a proof. So that's the idea. So this is the method we want to extend. And then, sorry, you check the first terms. And it turns out that S3 is larger than 18S2, so we're good. So the method is really to synthesize extra hypotheses, and so that you can get a proof by induction. There are other algorithms that I should mention to be complete for this part, mostly for recurrences of order 2. For initial conditions outside of a line, a bad line, then using continued fractions, Wacklin, Worrell, and co-authors have an algorithm that proves positivity. And then there was this preprint, again by the same galaxy of co-authors, where it's order 2 and the coefficients have degree 1 with your co-author Sertuch. Then, using linear relations of 1 period, they prove positivity. So they have an algorithm that proves positivity. But it shows you that you need sophisticated, or more or less sophisticated tools from number theory. And then there's the simple class, which is the one I will be looking at. The order is arbitrary, but we have dominant eigenvalue or root. And again, there will be the initial conditions, in the same way as here, they should be outside of the line. They will have to be outside of hyperplane. And the underlying tool is the Perron Frobenius theory for cones, and that's what a large part of this course will be about. So the cone-based approach I'm running late, but the proofs were at the end, and I don't like proofs, so it will be perfectly fine. So the cone-based approach, first you need to go in higher dimension, but that's very easy. If you have a linear recurrence of order D, you turn it into a linear recurrence of order 1 for this vector un, where an, this matrix, is a sort of companion matrix of the recurrence. And now your recurrence is just un plus 1 is an un. So you look at vectors in R to the D. And then if you enroll this recurrence, you get that un plus 1 is related to the initial vector of initial conditions u0 up to ud minus 1 by this matrix factorial. So this is what we'll be focusing on. And so the positivity now is that the vector un should stay in the cone R plus to the D. Right? All the coordinates are positive. An example of what type of proof we will construct. Let's go back to this AMM example, the monthly example, where you had this recurrence, and you want to show that for A larger than square root of 3, the sequence is positive. And this is the cone we'll be considering. Y, the second coordinate, is larger than A times x over 3. Remember that A is larger than the square root of 3, so it's positive. And so that's positive. So we want to be in this cone. So what I will show is that once a vector is in that cone, if you multiply it by an, it will stay in that cone. So multiplying it by an means you apply this. So you look at 2ay over 3 from here minus x over 3. And I want to show that it's larger than ay over 3, right? We shift. You had xy, and the next coordinates will be y and a new one. So I want to show that it's larger than ay over 3, so I take ay over 3 aside, and what's left here is ay minus x over 3. But y is larger than x over 3, so this is a squared over 3 minus 1x. And this is positive because x is positive and a is larger than the square root of 3. And this was positive by the induction hypothesis. So once you're inside the cone, you stay in the cone, and you have proved positivity. Again, provided your sequence enters the cone at one point. So you have to check initial conditions. So the first two, u1, u2, are not in the cone. But then if you look at u2, u3, this vector, it's in the cone, and you're done. So that's the cone-based proof. And for this example, at least, it's not as troublesome with algebraic numbers as the direct proof I had before. For the example I had before, this running example, I just want to show you a movie to give you an intuition of what we're trying to construct. So this is the recurrence, and those are the initial conditions. You can look at the first values. They're all positive. Looks good, but not quite a proof. So I have extra code here to help me show what's going on. And the end of the proof of positivity will be tomorrow. Can I make this larger? Not exciting. C'est pour les caractères. Non. C'est bien tenté, mais non. So what do you see? What you see here is the intersection of a sphere with the positive cone. And since I'm only interested in directions of these vectors, ui plus 1, ui plus 2, I will show just the direction. I truncate the vectors so that they're all about as the same direction. And you'll see if they're positive because they will intersect this thing. So we start with u0, u1, u2, and we construct the first few vectors, and we see how they behave. So this is the first one. The second one, the third one, it's still inside the cone. And then you see that they tend to converge to a direction. And that's the intuition I want you to keep. Since we expect that they will converge to a direction, we only have to find a cone around that final ray and prove that once the sequence is inside that cone, it will stay there. So that's the cone-based approach. So that corresponds to finding extra inequalities, the faces of the cone, that you'll prove by induction. There's this technical thing that I will focus on a special class of recurrences where the matrix has a finite limit. But you don't have to worry too much about this. So let me show you an example. The example from before, because all the coefficients have degree 2, then the matrix has a finite limit. And the idea is that for this type of matrices, the polynomial coefficients behave like a perturbation of the limit recurrence. So your intuition is guided by the constant coefficient case. And there are cases where it doesn't behave like this. For instance, here you have degree 0, 1, 1. So the limit matrix is not nice. But you can, for positivity, you don't really, you have a lot of freedom. So it's not of Poincare type, but then you'll construct another sequence, Vn, which is psi n un, where psi n behaves like roughly 1 over square root of factor n. And you see that with these initial conditions, it's clear that psi n is positive. So Vn is positive if and only if un is positive. So I just have to prove that this new sequence is positive. And then by closure property, I can compute a recurrence for this new Vn. And now you have degree 2, degree 2, degree 2, degree 1, but that's okay. When you divide by the leading coefficient, everything tends to finite limit. So you have a reduction like this to the Poincare case. The details, it's quite elementary, and the details are in this paper with Mark.
And so in this example, taking just 1 over factorial n was to neutral.
Right, yes.
Because then you have a 0.
You get something out of which you don't get any interesting information.
So finite here means like you have something that not possibility, but also maybe not 0.
Not 0. Yes.
This n plus 2 that defines sign, you obtain it by looking at the degrees in the first recurrence. Is the plus 2 for
yes, it's a matter of it's a Newton polygon construction. N minus 20 here, but then it's not positive.
Yeah, n plus 2.
N plus 20. Well, that would be okay, yes. Okay, so cone-based proofs. Again, A is the limit of my AN, and I want to do this, construct a cone around my sequence. That's what we work with Alaa. So the idea is to construct a formula that the vector enters a cone that's inside R plus 2 to the D, and then it will stay there. So we want to construct such a formula, construct such a cone. So first you check that you are in the right situation. Then you construct a cone that's contracted. When you apply the matrix to the cone, so except 0, then you go inside the cone, in the interior of the cone. So if it's contracted, it means that for n large enough, it's at least invariant. It's even contracted for n large enough. So you find an M such that for n larger than M, an of k is inside k. So that's step 2. And then you check the initial conditions, which means that you compute the values. If they are not positive, you're done, it's false. If the index is larger than this M that you found in step 2, and it's inside the cone, you're good, you've proved positivity. And then that's it. The only point which is delicate with this algorithm is that it may not terminate because of this infinite loop here. And the result is that it often terminates. It terminates for U0 outside a hyperplane. So mostly tomorrow, no, part of it today will be about how do you compute K, how do you compute M, and what is this business with U0? Why a hyperplane? And I should say that those cases where it's proved to terminate contain the cases proved to terminate by Cowers and Pilvine for order 2 and 3. And it works. Alaa has written an implementation for this. You give it the recurrence, the initial condition, and you say, oh, positivity. And it tells you yes. Or it tells you more than that. It tells you yes, the sequence is positive. Here is a cone where I give you the extremal vectors of the cone in the form of 2 matrices that could be simplified. That's the current state of the code. And starting at n equals 5, you are in the cone. So you get, that's for you, Khalil, you get a certificate. So, to summarize, the plan of the course is a long introduction. We are there. We're done with the introduction. Then, more information on matrices which leave a cone invariant. What are they? What can we know about them? And in particular, how do we compute K? This is related to something that's called the power method that I will tell you briefly about. And then we will go more deeply into this U0 tomorrow. Oops, with the generalized power method. And tomorrow there will be tons of examples. Because, okay, the method is nice when it works, but there are border cases where we can still make it work, and I will spend some time on pushing the boundary. Okay, so let's start with, okay, I'm 10 minutes late, so I will be able to skip some of the proofs. Matrices which leave a cone invariant. So now this is course mode, so you have definitions and proofs, and it's a bit more boring. That's how it is. Cones. I need a few definitions. What is a cone? A cone is a subset of RD that has this property that when you multiply by non-negative real numbers, you're still inside the cone. When you add 2 elements of your cone, the cone is convex. When you add 2 elements of the cone, you're inside the cone. And we'll use this terminology that's frequent in this area. The cone is proper when it doesn't contain the whole space, because that would not be interesting. It's solid. It contains the basis of the space. So it's not just a hyperplane, or a part of a hyperplane. Solid cone. And it's closed. I will only be looking at closed cones. And then we will have a cone and we will have a matrix. The cone is invariant by the matrix if, when I take a vector in the cone, I apply the matrix, I get a vector in the cone, and it's contracted by the matrix. If I take a vector in the cone, apply the matrix, and I am inside the matrix, even if my vector was on the boundary. Contract the cone. Okay. And it turns out that those properties can be characterized, can be seen on the spectrum of the matrix. So you take your matrix, you call the eigenvalue, the spectrum, the set of eigenvalues, say lambda 1, lambda r. The spectral radius, the largest modulus, will be denoted rho, as often. And I separate the dominant one, the large one, lambda 1, lambda nu, from the smaller one. For j larger than u, the modulus is smaller. Okay, what else do I need? I will, so there's a difficulty. We're working with real matrices, but we'll be using the Jordan form with complex entries. But still, we want to talk about real cones. So there's some technicality there. So the technicality is here, you take a basis where your matrix has this form of diagonal of Jordan blocks. Recall that a Jordan block has this shape. I will take the vectors in such a way that if I have two eigenvalues that are conjugate one to the other, not real, then I take the corresponding conjugate eigenvectors. So that when you add things, you get something real. And the dimension of this block is sometimes called, and will be called here, the index of the eigenvalue. Okay? So now, I have this matrix. I don't know about this cone, but if it exists, I have information on the matrix. If there's a cone that's invariant by the matrix, then first, up to relabeling the lambda I, lambda 1 is real and positive, and it's the spectral radius. And for all dominant eigenvalues, their index is at most that of lambda 1. So their blocks cannot be wider. And in that situation, the cone contains an eigenvector for lambda 1. Bless you. And that's a very nice result by Birkhoff in 1967. He does it in 3 pages. And I will show you the proof of this one because it's really nice. What else? There's an if and only if. Birkhoff proved the if part. I will come back to the only if. So that's for invariant, and for contracted, it's much simpler. Yes?
So if the matrix has a real eigenvector, I can always take the cone generated by just this one eigenvector. It's going to be invariant by the...
Oh, no, because it may not correspond to the largest eigenvalue. It has to correspond to the largest eigenvalue. You could have a real eigenvector for a smaller eigenvalue.
Yeah, but if this one eigenvector corresponds to the...
Yes, then it's inside the cone. No, it could be the opposite that's inside the cone. Because V1 and minus V1 are both eigenvectors.
Right.
So one of them will be inside the cone, yes. Okay, in the contracted case, it's much simpler. It's this condition that we've seen before. It's the easy condition to work with positivity. The first one is real, positive, and it dominates all the other one. And moreover, it's simple. The index is 1. And this is actually an extension of Birkhoff's result that was done by Van der Graaf the year later. And he also proved the converse direction. And that's the Perron Frobenius theory for cones, because think of the cone, you don't need light. think of the cone, I will write big. Is it readable? The cone R plus to the D. If you have a matrix with non-negative entries, then clearly when you give it a vector with non-negative coordinates, the result has non-negative coordinates. So it's invariant. This cone is invariant by that non-negative matrix. And then that's Perron Frobenius. The cone contains a vector with non-negative coordinates. If it's strictly contracted, it means that you take a matrix whose entries are all positive. Oh, that's a sufficient condition. Take a matrix whose entries are all positive. Then you take any vector, non-zero vector with non-negative coordinates, the image will be positive. So it's contracted. If you take the canonical vectors, their image positive. So it's contracted, and in that case, there's only a dominant eigenvalue, that's real, and a corresponding eigenvector inside the cone. That's Perron's part of Perron Frobenius. That was before. Okay, and this is an extension to cones. So let's get back to our gallery of examples. So I did something wrong. I didn't check. So I have this legend. If you have a circle, it's a simple eigenvalue. If you have a square, it's a multiple eigenvalue. Can you see that this is a circle and this is a square? Ah, some of you can. I will say it in each case. So what do we have? We have this exercise from the monthly. This is the picture. You have a dominant eigenvalue here, and the other one is inside the disk. So there is a contracted cone. The second one, that was the Straub-Zudilin example, again, same shape. There was this family, Gillis, Resnick, Zeilberger. For k equals 4, this is what it looks like, contracted cone. For larger k, 7, all the inner eigenvalues will converge to 0. So it's contracted cone, obviously. There's only one here, and it's positive. The example with Miyohara and co-authors, some of them in Rome, you have a simple dominant eigenvalue one here, a double one here, and then another one that's positive, contracted cone. The example with the nice picture, I find it nice, again, contracted cone. Turan's inequality, no. You have 3 eigenvalues of the same modulus. So you have an invariant cone, but no contracted cone. The example by Waknin with this 65 to the n, you have 9 eigenvalues on the dominant circle and 1 inside. So you have an invariant cone, but no contracted cone. Aline's example, you have a double dominant eigenvalue. So no contracted cone, but an invariant cone, but come back tomorrow. We'll see ways for this one. And the one by Meltzer and Metzaroba, also by Sergei and Aline, it's nasty. You have all the eigenvalues are double. There's one that dominates and 2 inside. And again, no contracted cone, but an invariant cone. So this is the first thing we do when we have an example. We look at the eigenvalues and check the picture. An application of this result, let me go back to the theorem. In this situation, I will show you the power method in this situation, the second one, when there is a contracted cone, when there is an eigenvalue that's real positive and larger than the other ones. So the power method is this nice method where you're interested in the largest eigenvalue of a matrix. You pick a random vector and you iterate this un plus 1 is a n un, and you normalize because for numerical reasons. And then, when you're lucky, which is this hypothesis, well, it's like in this picture. The vectors converge to an eigenvector of the matrix for the dominant eigenvalue. And I will prove it as a consequence of what we've seen. So that's, I will show more. I will show that if you take this matrix A, so it's a constant matrix, and I'm saying that A to the n divided by lambda 1 to the n, lambda 1 the dominant eigenvalue, that converges to a rank 1 matrix V times transpose of W, where V is an eigenvector of A on the right, and W is an eigenvector of A on the left. And then if you take U0, so you see now you start with your initial conditions. You're looking at A n U0. So you're looking at V transpose of W U0. So as soon as V transpose of W transpose of, wow, as W transpose times U0 is not 0, this will converge to a multiple of V. So outside of this hyperplane, the method works. So why is this a consequence of what we did? It's really more or less clear. Because you have only one dominant eigenvalue, your matrix is of the form lambda 1. Here you have zeros. And you have a block B. Okay? So that's A. So AN is like this. So AN divided by lambda 1 to the n, you have a 1 here, and you have B divided by lambda 1 to the n. Now you let n tend to infinity. Because the largest eigenvalue of B is smaller, this block, as n tends to infinity, it tends to 0. Doesn't mean that it decreases, right? At first it may decrease, but it tends to 0. So, so we are left with 1 block of 0, 0, 0, P minus 1, P. When you have this, you see that not all of those matrices are useful in the product. Because when I multiply 1 by 0, I see the first row of this, but I don't see the rest. So it's the same as having a line here and 0. I get the same result. And on the other side, it's the same, but for columns. Okay. So now so you get the rank 1 limit. That's clear. Now what about V and W? If I take U0 here, I'm claiming that this will be transpose of W. No, maybe clearer. Here, the first column of P is the dominant eigenvalue, eigenvector. So that's V. And here, it's by transposition, it's the eigenvector for W. And then we're done. So I insist on this, because that's okay, we have a proof. And that's what we will want to extend to the case where it's not a power a to the n, but it's this factorial matrix, an minus 1, a1. Because I remember in general, when we are not in the constant coefficient case, we have un plus 1 is an un, and thus an minus 1, A1, U0. A0, U0. Okay? So tomorrow we'll spend a lot of time in trying to extend this, and that's what will be called the generalized power method, and show that again there's convergence to a rank 1 matrix. Ooh, by looking at more geometry of cones. Okay, so that's what I told you. Step of the proofs on the next slide will be skipped. They are in the slides that you can recover from here. So it's not difficult. You can read the slides. I mean, a proof in by slides is always messy, and anyway, you believe me. And those proofs, except for Birkhoff's, that's nice, are often by contradiction, and you don't get much insight from a proof by contradiction. So this one, maybe, no, I want to give you time to breathe. Then bloop, 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 bloop. We'll see a type of geometry tomorrow. Bloop, bloop, bloop. The reciprocal, no, this one I will need. The reciprocal is I can construct a cone that's contracted by the matrix when it has those properties. So I will show it first on an example, the same example. This is our matrix. This is the eigenvalues. You see that lambda 1 is larger. And this is the picture. And this is the cone, a cone that works. You take the dominant eigenvector, you multiply it by a real A and a real mu. You take the two conjugate eigenvectors, you multiply them by a complex B and its conjugate, so what you get is real, and you restrict to the absolute value of B smaller than A. And then it's easy to see that for all mu, if you multiply by A, you stay inside the cone. Why? Because V1 is multiplied by lambda 1, that's bigger than the other ones, and V2 and V2 bar are multiplied by lambda 2 and lambda 2 bar that are smaller. So this condition will be even more satisfied with a strict inequality instead of a weak one. So that's why we're inside. And also, V1 here has positive coordinates. So if I take mu large enough, you know, I stretch it and I add the small piece with the V2, then you are inside R plus 2 to the D. Okay, so I will skip the general case, but it's really what you've seen is the general case. Well, you have to be careful with the Jordan part. So back to the algorithm. Step 1 was construct a cone. You use Van der Graaf's construction, for instance, but we'll see tomorrow other variants of it. Existence of M in step 2, we'll see how we can compute it. And then there will be this business about generic U0. And that's it for today.
So thank you so much, Bruno, for this wonderful class. And questions, comments? Oh.
There's one in the back.
One in the back?
Or you can shout it and I will repeat it.
So maybe a very naive question is, so this difference says that in the very technical case that there is a simple root, simple dominant root, the algorithm still terminates. Do we have an idea of the, let's say, complexity of this algorithm? With the green equation?
Okay, so let me repeat because it's recorded. So the question is, this is all nice, but what about the complexity? More or less. So there are two parts. There's one part that depends on the matrix only, and one part that depends on the initial conditions. For the part that depends on the matrix only, constructing a cone, well, you have this Jordan business, so no. We'll see tomorrow that we don't need the exact Jordan basis. So we can do numerical approximations. Then, of course, you have to worry about the distance between the dominant eigenvalue and the other one. But once this is fixed, you should get polynomial complexity in your in this for this part. For the second one, for mu, in the case where you don't have any parameters, it will, I'll show that in more detail tomorrow, reduce to simple inequalities in one variable, polynomial inequalities in one variable, and the complexity for this should be, again, easy enough, but again, probably the distance between the two dominant eigenvalues play a role. And then for the last part, this U0, it really depends on how close your vector is from this bad hyperplane. And this has not been formalized in such a way that I can tell you, oh yes, if you are at distance more than this, then a finite number of steps will be okay.
I had a question. So first, thanks a lot for the talk. Did you investigate a possible connection with Krafft-Schick method in interval arithmetic? Because it looks very similar. Like you have boxes instead of cones, and you look for a contracted box, and it's related to the spectral radius of the matrix being smaller than 1. So there is some similarity.
So the simple answer is no, because I was not aware of it, but we should.
Thank you.
Any other?
Yeah, there's Pierre.
Oh, sorry.
And in your algorithm, why don't you output a hyperplane out of which U0 must not lie?
Ah, that's a beautiful question. I don't know if you know the answer. It's because we don't know it. We know that it exists. I will show you tomorrow why it exists, but it's not a constructive proof. And I will show you why we don't expect it to have a constructive proof.
I was not sure.
So I think it's time to thank Bruno again, and then.